Hello and welcome to this video for A-Level Physics in the OCR specification in the module of forces and motion and in the subchapter of forces in action, looking at the topic of Archimedes Principle. So in this lesson we're going to look at Archimedes Principle and how to apply Archimedes Principle to different situations. So if we've been successful and learned in today's lesson, we should be able to state what Archimedes Principle is, detail how upthrust is produced, and know how to calculate upthrust and pressure in fluids. So we're going to look at the following part of the OCR A-Level Physics specification, 3.2.4, density and pressure, and we're going to be looking at particularly at C, which is pressure is equal to h rho g, the upthrust on an object in the fluid, and Archimedes Principle. Now, look at the following schematic diagram of a dam. This is an example of an open system of a fluid. So think about the following. How are dams constructed and why is this? Now if you look at the picture, you'll notice that dams are constructed with a thicker wall at the bottom and a thin wall at the top of the dam. That's because fluid pressure changes in an open system. So it's a fundamental concept of pressure. Fluid pressure changes in an open system, but it stays the same in a closed system. So you can see here that there is a low pressure at the top of this liquid, which requires a thin wall, whilst there's a high pressure at the bottom of the liquid, so requires a thicker wall. So we can see very quickly that fluid pressure increases with depth in an open system. So as we move down the wall, there's an increasing pressure as we go to a greater depth of fluid. So this shows us that in open systems, the pressure of a fluid increases with depth. And this can be shown in larger areas of water, like an ocean. So you can see here that there is a liquid and the force being placed downwards increases the lower you go, as there's an accumulative effect from the particles above it. So this downward force that's being produced is weight, and the further down you go, the more particles there are above you in the fluid, so the greater the weight above you. So you'll see at the top of the fluid it's got a lower pressure, because there are only a few particles above that particular point pushing down, so the weight pushing down at that part is low. But at the bottom we have a higher pressure because there are more particles above that point pushing downwards, so the weight pushing down is high. So we can see that as we move down our fluid, that the weight of the fluid acts downwards on an object increasing with depth, and the pressure acting downwards on the object increases with depth, because the lower you go in any fluid, there are more particles above you pushing downwards from the collisions that they make. So what this actually means is that at any horizontal line in a diagram of a fluid, the number of particles above that point is roughly the same. So it tells us that along that particular line, the pressure along it is constant. Now when this is considered in air as a fluid, the horizontal line of constant pressure is called an isobar. Now it's important to note that areas of different pressure can exert a force on objects in the fluid. So if you're at the bottom of the ocean, a force is exerted downwards, pushing you down. So to clarify, in an open system, the fluid pressure increases with depth. That's because the further down in a fluid you go, the greater the number of particles above that point producing a force downwards. Now in an open system, the fluid pressure is constant in a horizontal line of the same depth, because along this line there's the same number of particles producing the same force pushing down. Now a difference in pressure can cause a resultant force on an object, which can be calculated with our equation of a resultant force is equal to a change in pressure times by the area. Now this concept is shown in the following diagram. Now you can see in this particular image that because pressure increases with depth, at the top of the column there is a lower pressure, so you get a little spurt of water, but at the bottom there's a large spurt, so there's a higher pressure. Why is that? At the top there is less weight above it pushing down, and at the bottom there's a higher pressure because there's more weight above that point pushing downwards. Now we can calculate the pressure in an open system with the following equation, that the pressure change in pascals is equal to the change in depth in meters times by the density of that fluid in kilograms per meter cubed times by the strength of gravity in meters per second squared. Now this equation calculates how the pressure changes when an object moves from one position to another in the fluid. Now the equation of pressure in pascals equals the depth in meters times by the density of the liquid in kilograms per meter cubed times by the strength of gravity calculates the pressure at one point in the fluid. Now we can derive this as, consider the following column in the fluid. The pressure at the base of this particular column is going to be force over area, so therefore the force in this instance is weight, so the pressure is weight over area. Now we know weight is equal to the mass that's in the column times by g, the strength of gravity. Now we also know that mass is also equal to density times by volume. So weight is density times by volume times by g. Volume is the area times by the height, so it is it's going to be rho times by a times by h times by g. So therefore pressure is going to be this value for weight over area, and you'll notice straight away that the a's cancel through, so therefore pressure is equal to rho gh, or density of fluid times by the strength of gravity times by the depth. Now this equation tells us a few things. Pressure does not depend on the cross-sectional area of the object. Pressure does increase with depth. Denser fluids exert greater pressures, and that the pressure for a fluid at a depth is the same in all directions. So let's have a look at an example question. Calculate the pressure due to seawater of density 1050 kilograms per meter cubed at a depth in the sea of 200 meters. So we can calculate the equation. Pressure with the equation pressure equals depth times by density times by strength of gravity. So 200 times by 1050 times by 9.81, so pressure is equal to 2.1 times 10 to the 6 pascals. Now, if an object is less dense than the liquid it is submerged in, it will float. So the density of an object determines if it will float or sink. So if an object is denser than the liquid it is submerged in, it will sink. Now, why does density determine if an object floats or sinks? How does this link into forces on an object? So the buoyancy of an object depends on the forces that act upon it. An object will float if the upthrust being produced is equal to the weight. That's because the forces on the object in the vertical plane are balanced. There's no resultant force. However, an object sinks if the weight is greater than the upthrust. That's because the force on the object in the vertical plane are unbalanced. There's a resultant force downwards. Now if the upthrust were greater than the weight, then the object would accelerate out of the liquid as there would be a resultant force upwards, but this can't happen due to how the forces are produced on the object, and upthrust would only be produced when submerged in the fluid. So what actually causes upthrust to be produced on an object immersed in water or a fluid? Well, it's linked into what we've just looked at. When an object is in water, there's a greater pressure on the object at its bottom than at its top. This difference in pressure makes the object push up. It creates a resultant force called upthrust. So because there's an increase in pressure the further you go down, there's a higher pressure at the bottom of the material compared to the top of the material. Now this produces the upthrust, and there's always a force exerted going from the higher pressure to the lower pressure. Now like we said, for all liquids pressure increases with depth, because the further down you go, the more particles above you pushing down. Now we can calculate upthrust as the force on the top surface is pressure times by area, so it's rho gh times by A. Whilst the force at the bottom surface again is pressure times by area, so it's rho g times by h plus x, the increased distance, times by A. So the resultant force is the two forces subtracted from each other, so it's equal to A rho gx. So that is what our upthrust is equal to, A rho gx. So the volume of a block of fluid displaced is AX, and it has a mass of AX rho g. Now, An object that is less dense than the fluid it is placed in weighs less than the equivalent volume of the liquid. Now that's very, very important because it means that it displaces a volume of fluid that is equal to its weight. So therefore upthrust equals weight, and it does that before it is completely submerged in the fluid. So an object that's denser than the fluid is placed in will weigh more than its equivalent volume of fluid that it would in theoretically displace. This means that the object is unable to displace enough fluid to equal its weight when it's in the actual fluid. So this means that the weight is always larger than the upthrust, so will always sink. So this leads to the concept of Archimedes' Principle. This is that the upthrust exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces. So for an object to float, the weight of the object must be equal to the weight of the fluid it displaces. Now, an object will float on a fluid if it has a lower average density than the fluid, because the object will only displace a volume of fluid that weighs as much as the object does. The volume of fluid is lower than the volume of the object due to the different densities, so it will be partially immersed when this occurs. But if the object is denser than the fluid, the water it displaces will always weigh less than the object itself, causing it to sink. So for a floating object, we can write this mathematically, as we would say h2 minus h1 rho Ga equals rho Vg, because you can see that the change in height times by the area is the volume, that will equal the weight of the object, which is mg. Now let's just quickly look at the idea of air pressure. Now if you live in the atmosphere of the Earth, you're constantly surrounded by the particles of the air. Now these gas particles constantly move about at random. The air is a fluid as it can flow since the particles are able to move around. Now in this motion, some of the particles will collide with the objects present. And when it does this, these collisions will cause a force to be exerted on those objects. This produces a pressure which we call the atmospheric pressure. Now the pressure means that the force is exerted at right angles to any surface which the particles will hit. Now atmospheric pressure works in the same way as the fluid pressure in a liquid discussed previously. At the top of the air gas, there are few particles above pushing downwards exerting a force, while there are many particles above pushing downwards exerting a force when you are at the bottom of that gas at the surface. So at the top of the atmosphere we have a low pressure, and at the bottom of the atmosphere near the surface we have a high pressure, which you can see in this diagram. So the higher up you go in the atmosphere, there is less weight pushing downwards exerting a pressure. But there's also a second reason why this takes place. There are fewer particles pushing down as you are higher up in the atmosphere, and at this point there are fewer particles in the atmosphere in general. So there are fewer air particles in total above the point you are measuring. That's because the atmosphere has become thinner the further up you go, because the particles are further apart. So we can also say that the density of the atmosphere has decreased with altitude. There are fewer air particles per cubic meter. So remember, there are two reasons why the pressure will change in the atmosphere: the number of particles present and the amount of force acting downwards. Also note, although we measure the height from a surface when we calculate atmospheric pressure, we do not look at depth. So this means the atmospheric pressure decreases with height. So when you go to high distance from the surface, the pressure is low. And when the distance from the surface is low, the pressure is high. Once again, why is that? Because there are fewer particles above producing a weight downwards, and the particles are further apart. Now pilots know this. The higher you fly, the lower the pressure of the atmosphere is. At the top of Ben Nevis, the highest mountain in the UK, the air pressure is 87 kilopascals as opposed to 101 kilopascals at the surface of the Earth. So, atmospheric pressure is created on a surface by air molecules colliding with the surface. The greater the number of particles above a point in the atmosphere, the greater the weight acting down from the particles, the greater the pressure. And there are fewer particles higher up in the atmosphere producing pressure as they're further apart from each other. So as height increases or depth decreases, the atmospheric pressure decreases. So that brings an end to our lesson today, where we looked at pressure is equal to density times by the strength of gravity times by the height. We've looked at upthrust on an object, and we've looked at Archimedes' principle. So if we've been successful and we've learnt in today's lesson, we should be able to state what Archimedes' principle is, detail how upthrust is produced, and know how to calculate upthrust and pressure in fluids. So thank you very much for watching this lesson for the A-Level Physics OCR specification in the Module 3 chapter of Forces of Motion, the subchapter of 3.2 Forces in Action, and finally the topic Archimedes' Principle. Thank you very much and have a lovely day.